Okay, we have our midterm exam on Wednesday, right? The midterm will cover pretty much everything that we've done, but not this, right? Not 11.8, but I said I would start 11.8 today. I gave you some problems to review, to go back and take a look at, but you should be looking at your homework problems. You should be looking at the problems that I did in class. And you should be all right on the midterm. Remember, the policy that I have in the syllabus about the midterm and the final, you must score 50% or higher on the midterm or final to pass this class. So if you score below a 50 on the midterm, you automatically have an F in the class, and that's it for you. Okay, that's because people have been asking me, like, why do I have that policy? The reason is because everything that you've been doing is take home. So there's really no way of me knowing who's doing it. Like, I trust that everyone has integrity, that you're doing your own work. But if you're turning in, good grades on all your take-homes, and then you come in, you get a 20 on the midterm, then I'm going to start to question whether or not that was really you doing all that work at home. So it's just so that there's some accountability. You have to at least know half of the material on the midterm, okay? But I don't want that to be a surprise either. If someone gets like a 40 on it, and I'm like, hey, you need to drop the class. I don't want them to be surprised. Okay? All right, so we are going to start 11.8. This is one of my favorite sections in the entire book. I'm not quite sure why I like this section so much, but I do. And it's going to be some algebra. There's going to be some algebra in this section that gets a little bit messy, but more importantly, what we have here is really one of the first times we really have to think like logically about trying to check whether or not things are true or false. And like, when do you know you're actually done checking? And so this is the first time you're ever going to see something like this. It's difficult to get thorough with this method. So I'm going to try and point out all these little things I'm talking about right now as we move through the examples. This is called Lagrange multipliers. It's the section. And it's just an absolutely wonderful result. So let me bring it up here. Okay, so far what we've done in the last section is that we know that we can find local maximums and local minimums of functions of two variables, right? Surfaces on their implied domains, and that's when we used capital D, right? Then at the end of the section, you had to go and try and find the absolute maximum or minimum of a function of two variables on some closed bounded region. So that's where you had to move along the edges, right? That's what we did last class? Yeah, y'all okay? Hello? Is this working? My mic working? Okay, we now develop a very powerful method for finding the maximum and minimum values of a function subject to a constraint. So what does that mean? Subject to constraint. Well, here's the method, and then I'll show you a picture. So this is a method of Lagrange multipliers for two variables, meaning that we have a function of two variables, and we are given a constraint. Now we're going to call this a constraint equation, and it is also, it has two variables in it. Okay, so you have some equation over here that involves two variables and a constant. If we want to find the maximum or minimum values of this function when we restrict ourselves to this constraint, then this is what we're going to have to do to figure it out. Do you remember when we were trying to find the local max and local min? We were finding, we set those partials. Remember we set the partials equal to 0? Do you remember that when we were computing D? We did this, we figured out what x's and y's made these both true, and then we calculated D, right? Took these points and calculated D. This method says we can still find these x's and y's, but what we're going to do to get them is going to be a little bit weird. Okay, what we're going to do is this. We are going to find all values of x, y, and the Greek letter lambda that make these two things true. First, the gradient of f must be equal to lambda, which is a constant, times the gradient of g. Do you all remember that the gradient vector, right, is a vector, yes? Gradient is a vector. This is a vector also. And if I'm saying that this vector is equal to lambda times this vector, then what can you say about these two vectors, the two gradients? They're parallel, right? That's what it means. They're scalar multiples of one another. So for some reason, the places we're going to have maximums or minimums of this function happen when the gradient of this function is parallel to the gradient of our constraint. I'm going to try and show this to you visually later. For now, you're just going to have to believe that it works. So we have to satisfy that equation, and we also have to satisfy the constraint. All right? We will evaluate the function at all the points that satisfy these two things. The largest is the maximum, the smallest is the minimum. Now, when we say that we need the gradient of f to be equal to lambda times the gradient of g, remember the gradient of f is just the partials? So this is the gradient of f. This is the gradient of g times lambda. So I passed the lambda through. We want these two to be equal, so what we do is we just set the components equal to each other. So it turns out, end of the day, okay, at the end of the day, when you're trying to figure out how to do Lagrange's method with two variables, you need to be able to satisfy three equations, and here they are. If you can satisfy those three equations, you're in business. And the end of the notes here, I remind you of what those three equations are going to be. Here they are. Okay? Y'all got it? This is what I'm about to use through the next few examples. When I have three equations, right, I'm also going to have how many variables? Three. What are they? X, y, and lambda. So I'm going to have three equations. I'm going to have three unknown variables. I need to find the solution set for that. And these are not necessarily linear equations. These could be nonlinear. So we can throw all the matrices stuff out the window. Okay, so let's get an idea visually what's happening. I want to find the maximum and minimum values of this surface, all right? So just by looking right now, if I don't restrict the domain and just let its domain be whatever its domain is, its implied domain, does this have a minimum value?
Yes.
Yes, it would be down there at the very bottom, right? What would be the maximum value? Well, I had to stop my picture. We have to imagine that this keeps going, right? So there would be no maximum, would there? Like if this thing just opened up forever? It would have a lowest point, but it wouldn't have a maximum. Yes? Okay, so f of x just by itself has a minimum value but not a maximum. But what if I just restrict it to this? What does it mean to constrain it? This is our constraint here. I'm looking at the maximum minimum values of that function just on x squared plus y squared equals 1. You recognize that? X squared plus y squared equals 1? It's a circle, right? That circle would live in two-dimensional space. It would be on the xy plane, right? In three-dimensional space, what's x, y, z? X squared plus y squared plus, x squared plus y squared equals 1. What's that in three-dimensional space? Cylinder, right? So what we're imagining is we're taking all the points that lie on that circle, right, on the ground, that's our domain, and we're just mapping those points into the surface, okay? If you're just allowed to plug those in, see, that's where we're constrained, our domain is constrained there. Then what we get is where that cylinder comes up and hits the surface, right? See the blue? That's where the cylinder hits the surface. And I can take the surface out of there completely. And so what we're looking for is the maximum and minimum values of this blue curve. Where do they happen, right? We have, it looks like 2 maximums, right? And 2 minimums. Where do they happen? That's the question. Understand? Where do they happen and what are they? Any issues visually with what's going on? No? We're good? Okay. Is that different than what we did last class? Are we finding the local max and mins on its implied domain? Are we doing that here? No, we're not at all. We are actually being very specific about its domain. And we are restricting its domain just to a circle on the ground. See how that's different than the capital D thing we did? Now, is it similar to the thing that we did with closed-bounded sets? Is it similar? Remember for a closed-bounded set? You have to have all the stuff inside and the edges? Is this a closed-bounded set? Is it? It's just the edge. Do you see that? So this is not what we did before. It's not the implied domain. It's not a closed-bounded set. This method's really good for finding the edge part of it, though. Understand? You good with that? Okay. We're about to see. Regardless of whether or not you understand the geometry of what's going on, let's see if we can do the math. So this is a function of how many variables? 2 variables. I'm subject to a constraint. I'm going to be using Lagrange's method, okay? Lagrange multipliers. Because I have 2 variables, I know I'm going to set up 3 equations, right? Equation 1, which I'm going to label 1, is going to be the partial of f with respect to x must be equal to the lambda times the partial of g with respect to x. By the way, what's the g function here? X squared plus y squared, just that part. Okay, the constant on the other side doesn't matter. G is the part that has the x's and y's. Just make sure, if this equation's weird, you got x's and y's on both sides, make sure you move everything to one side, all right? Okay, so that's the first equation I have to set up and satisfy. The second equation, I'm going to erase that g thing from there. It's in my way. Is partial of f with respect to y must equal to lambda partial of g with respect to y. And then the third equation is what? It's the constraint equation, the whole thing. So now let's actually figure out what this is. What is the partial of f with respect to x? That's partial of this one with respect to x, which is 2x. That must equal lambda times partial of g with respect to x. What's the partial of g with respect to x? 2x, so lambda times 2x. All right, I'm going to kind of separate these. Okay, that's my first equation. My second equation, what's the partial of f with respect to y? 4y must equal lambda partial of g with respect to y, 2y. And then my third equation, I don't need to touch that, okay? That just has to be true. The reason why this has to be true is because that's what's going to keep me on the constraint, on the circle, right? All right, we have some equations here. Let's see if we can do some stuff first that we know for sure is legal. I can divide both sides here by 2, right? I get x equals lambda x. I can divide both sides here by 2. I get 2y equals lambda y. Are we comfortable with that? I'm working with these like that. Everyone good? Now, we need to find an x, a y, and a lambda that make all 3 of these true at the same time. So let me first try to see if I can figure out something from the first equation. So someone might say, well, divide both sides by x and you get lambda, right? But if you divide both sides by x, what are you also promising me? X cannot be 0, right? So you've eliminated one of the solutions. What did I tell you? I know I told you about this. Don't do that. I said what instead? Don't ever divide by a variable that you can't control. What did I say to do? take it all to one side. So let's just move the lambda x to the other side. And now you can do what? Factor out the x, right? So if I factor out the x here, I get x, and I get 1 minus lambda equals 0, right? Okay. This is where I was telling you at the beginning of class. The part of these problems that gets weird, that you get points taken off for, is that you'll get answers, but then you forget that there was other stuff you were supposed to look at. So I'm just going to focus on that right now. Okay, this is my work over here. I'm going to start writing logical steps here. Okay, ready? What did I say this was? Oh, I forgot to set these equal to 0. Sorry. X equals 0. And then this, if I set that to 0, I get what? Lambda would have to be 1, right? So to satisfy the first equation, x would have to be 0 and lambda would have to be 1. Yes? All right, I have to look at both of those scenarios. So I'm going to start with the first one. Suppose that x is 0. What can you tell me if x is 0? That y squared must equal 1, right? So what I'm going to do is this. Suppose x equals 0. Then 3 implies, so I'm telling you now, to look at equation 3. If x is 0 there, that equation implies what? Y squared must be 1, which means y equals plus or minus 1. Agreed? Also, within this same framework, can you tell me what lambda would be? Because right now, here's what we have. We have x is 0, y could be 1, and then I'm going to do it this way, x, y, lambda. Okay, tell me, this doesn't live in three-dimensional space or anything. This just, I want to know the value of x, y, and lambda. I have that scenario, and I have this scenario. So let's see if we can figure out what lambda would be in this first one. If x is 0 and y is 1. So if x is 0, this is true, right? Okay, come over here. If y is 1, what would happen? From equation 2, what? 2y, I'm sorry, y is 1? Isn't y 1? Okay, so this would be 2 equals lambda? 2 equals lambda. So I could say that's 2, right? Understand that? How about this? If I assume that the y is negative 1, then what would 2 give me here? Negative 1, negative 1. We get negative 2 equals negative lambda, so still lambda's 2? You following me? So far from Lagrange multipliers, here's what I know. If x is 0, then y has to be plus or minus 1. If x is 0 and y is 1, then lambda's 2. If x is 0 and y is negative 1, lambda's 2. So these three should work, yes? Or these three triples, or these two triples should work. Okay. Done with that thought. That was x0. Now, let me suppose lambda's 1, because if lambda's 1, this is also satisfied, isn't it? So now I'm going to start a new thought over here. I'm going to erase this. Do you see how people might work through that? Get this out, get those points, and then be done? And then move on to the next problem and realize, look, you never checked lambda was 1. And that you'll lose points for. Even if you get the right answers, if you don't check all of them, that's a mistake. All right, so suppose now that lambda's 1. What would you like me to look at? If lambda's 1, can I figure out what x and y are? Well, what does the first equation turn into? If lambda's 1, go to here, right? Go to right here. If lambda's 1, then x is x, right? Does that help? X is x. Okay, so x can just be whatever it wants to be. All right, what about 2? Does 2 give us anything? That 2y is equal to what? y. Now that's different. X is obvious, right? Look, x is x. Everyone agree x is x? But that doesn't tell you shit, does it? 2y being y, now that's different. Subtract y from both sides. And what do you get? Y is, come on, we can do it. Subtract y on both sides. Y is 0. Now that's concrete information, right? Y is 0. The only time a number will be equal to double itself is if it's 0. That make sense? Okay, now if y is 0, now you have a little more information. What can you do? What can you conclude? Go to the third equation. What does the third equation tell you? That x squared plus y squared, which in this case would be 0, would be 1, right? And that means that x would have to be plus or minus 1. So now we have two other situations to look at. We know that x could be 1, y is what? 0, and lambda's 1. Or I could have x is negative 1, y is 0, and lambda is 1. Understand? This was all under the framework of lambda being 1. So this was always 1. When we worked through this, we knew y would have to be 0. And once we said that, that gave us two values of what x could be. So this is all within another thought. Got it? Okay. Are we done? We looked at this, right? Okay, what about this one though? What if you would have done the same thing that we did here for this one? Bring the y over to the other side. You would get 2y minus lambda y equals 0, right? Factor out a y. Get 2 minus lambda equals 0. You agree? And so we have two possible answers here. Y could be 0 or lambda could be 2. Well, guess what? We get to go look at those now. But one of them's actually not that bad. Because what if y is 0? Didn't we just do that? Didn't we just do that? But I'm gonna go through the process. Suppose y is 0. If y is 0, then the second, well, no. Y is 0. What can I say? From the third equation, this is true. So I'll say from the third equation, I know that x must be plus or minus 1. Agreed? So I have this right now. I have y is 0. X could be 1. X could be negative 1. Do you see I'm repeating myself? I've actually done this work. But is our lambda going to be any different? If x is 1 and y is 0, what's lambda? Try it out over here. X is 1, y is 0. How about this? X is 1. What do you get? Lambda's 1, right? Doesn't that match what we just did a second ago? Yes? Back when we let lambda be 1? And then what about if x is negative 1 and y is 0? Negative 1, you get negative 1 is equal to negative lambda. That's also 1, right? So I've repeated myself. If this were a test or something, I wouldn't expect for you to necessarily go through this again, but I would expect for you to write this down. And then down here, you could just be like, okay, we already took care of that, right? All right. But what we have not done is looked at lambda being 2, have we? You ready to see lambda 2? Suppose lambda is 2. Or did we do that? Did we get lambda 2 earlier? Yeah. We did. Okay, so when lambda was 2, that's when we had x was 0, didn't we? So go back and look. Lambda 2, see previous work. We had 0, 1, 2, and 0, negative 1, 2. Is that right? Yeah. Is that what we had earlier? Okay. So we've already done this. You got it? So at the end of the day, there are four pairs of x and y coordinates we need to look at. The lambdas are not important when we're going back and trying to figure out where the max and min are. The lambdas are important for us to be able to solve the equations. We need 3 variables to solve for 3 unknowns. So this is just part of us getting x and y. So we are now going to look at and compare the following. We have to look at f of 0, 1, f of 0, negative 1, f of 1, 0, and f of negative 1, 0. Right? Those are the x's and y's that we had without the lambdas. What's f of 0, 1? Going back into this function. 2. What's f of 0, negative 1? 2. F of 1, 0, 1. F of negative 1, 0, 1. So this right here corresponds to our minimum. And this, because they're the same numbers, this is our max. So what is the maximum value of this function if we constrain ourselves to that circle? What's the biggest value it ever attains? 2. And it happens at 2 different x and y values, right? If x is 0, y is 1. Yes? And then the smallest it'll ever be would be 1. Does that make sense? Okay. That was the easy example. This one's still easy. So look at this one. Find the maximum and minimum values, or minimum, of this function. Same function, right? What's different? It's an inequality instead of an equation, which means now you're looking at the entire disk, right? Your domain is now, everything on that disk can get plugged in, right? Not just the edge, everything. Lagrange allowed us to do the edge, right? We still need to do the inside pieces now. How do you think we can do the inside pieces? With the capital D, right? Actually, we don't need the capital D. We just need the method, which was to set the partials equal to 0. Remember, when we set the partials equal to 0, this gives us candidates to get plugged into D, right? But from last class, we learned that, look, if we figure out where these happen, and then if we have to move along the edge, what we can do is just compare all these answers. Make sure that these points live in our disk, and then from there compare. Now, what does this look like geometrically? What's different? When you compare that, you see the difference between this and the previous problem? Previous one was just moving along this edge. Now we're allowed to have all that junk in the middle. So when we look at it from the top, it should look like a circle. Okay, so this is going to have a maximum, yes? Should be the same 2 maximums we had before, right? But the minimum is no longer these 2 points, right? It's this point. So how do we find that? Well, we just set the partials equal to 0. So all we're doing is just adding one more layer onto this problem, right? We've already done the edge. Now let's do the inside. So just set partial of f with respect to x equal to 0. This is going to be a very simple one to solve. What is it? 2x equals 0. What's the solution here? X is 0. So that's how we set the first partial equal to 0. Now you do the partial of f with respect to y equal to 0. That's 4y equals 0. And so y equals 0. So the only way to get the 2 partials here equal to 0 is to let x be 0 and y be 0, which gives us a point 0, 0. So you remember just a second ago when we did Lagrange, we did 0, 1, whoa, 0, negative 1, 1, 0, negative 1, 0. Now we have one additional point to check, 0, 0. Understand? So this was all Lagrange. This is the thing from here. And when we plug in 0, 0, we get 0. And that's now our new minimum, right? These are no longer your minimums, because those came out to be 1s. That's it. Nothing else on that one. Okay? Questions?
So we always have to do those four and then before we get from our equation?
Say again?
Do we always have to check those four first and then whatever we get from the given equation?
Oh, no, you can do them all at one time. You could do the other one. Everything is going to be dictated by what your domain is. What is your restriction? If your restriction is just along an edge, a boundary, Lagrange, right, is all you'll use. If it's the boundary and everything inside, then you'll need to use some combination of both, or do what we did last class where you just like do L1, L2, and move around the edges. If there's no restriction on the domain, then you have to do capital D to get local max, local min. And that's all you're doing is finding local, not global. Is that kind of clarified a little bit? Okay. All right. We're going to do this one. We'll look at it in a minute. All right. Again, please pay attention to organizing our thoughts properly, taking the different scenarios. Find the maximum and minimum values of the function f of xy equals 4x plus 6y with the constraint that x squared plus y squared is 13. I will have how many equations that I need to satisfy here? 3 equations. The first one is partial of f with respect to x must equal lambda partial of g with respect to x. The next equation, partial of f with respect to y must equal lambda times partial of g with respect to y. The third equation is the constraint, x squared plus y squared must equal 13. And keep in mind that what I circled in blue there, that's g, right? Aren't we plugging in just points on a circle again, just on the edge? And we're plugging those into this function. Anyone know what this function draws? It's a plane. That's right. It's a plane. That's the same as saying like z equals 4x plus 6y. Everything's linear. All the variables are linear. You should draw a plane. All right, well, here we go. First equation, partial of f with respect to x. Oh, that's clean, right? 4 equals lambda times partial of g with respect to x. So partial of this with respect to x is 2x times lambda. So can I write 2 lambda x? All right. What's the next one? Give me the next equation, someone. 6 equals 2 lambda y. Okay, good. And then the last one, there's nothing to do. Let's scale through just to clean them up a little bit. This is 2 is equal to lambda x. This is 3 equals lambda y.